So let's talk about inferences. And we're going to start with inferences about proportions. And the first thing we're going to do is we're going to do um, confidence intervals for these. So let's watch the central limit theorem in action for a proportion. Okay, so here we are back at stat key, but now we're going to look at proportions. And so let's look at college graduates in the US. And notice that in the original population, the proportion is 0.379, okay, or 37.9%. So now the idea is that we want to be able to take a sample and make a good inference, i.e., educated guess, about what is happening in the population when we don't know what the population number is. So let's generate one sample. So it's a sample of size 50, and 21 were college grads. And so the sample proportion is 42%, 0.42. Notice that's a little bit higher than the population proportion. And we know that none of our samples are perfect, right? So again, let's generate a bunch of samples. There's 1,000, 2,000, 3,000, 4,000. And notice how quickly this starts to look like the standard normal curve, right? Notice that now we have 8,000 samples. Oh, no, now we're up to 12,000. And notice that the mean of the proportions in these is 0.379, which is the population proportion. Okay, so again, if we had repeated samples over and over again, eventually they would conform on the population parameter, but we only have one sample. So that is the problem. Okay, so what does that central limit theorem let us do? It lets us say things about the population parameter based on a sample. So the first case we're going to undertake is for proportions. We're going to do confidence intervals and hypothesis tests. First, we're going to do confidence intervals. So we're going to learn two methods for doing this. One is sort of a standard approach based on the tables of probabilities and the standard normal curve. Remember we said as the sample gets large enough, we can use the central limit theorem, and so that is an underlying assumption in this model. Then we're going to learn another approach called bootstrapping, and that relies less on the underlying theoretical distribution, and it's more based on the data in front of us and using simulations. So first, the standard approach with our table. And remember for our standard normal curve, right? So our Z curve, our friend here, if we want 95% in the middle, that means we have 2.5% on each tail. And our magic numbers in Z terms for that is minus 1.96 and plus 1.96. Okay, so for our sample statistic, we will construct a confidence interval. And what we say is that we are, in this case, 95% confident that the population parameter, that is the population proportion, falls within the interval that we define. Okay, and so the formula for doing this for proportions is we start with a p hat or p bar, doesn't matter. People sometimes use those interchangeably, plus or minus the z-score for whatever level we want, so in this case 95%, times some measure of the standard error. And if you had a population proportion, you can use it, rho, but you can also just use p hat, p bar, 1 minus p bar from your sample over your sample size. Okay, so there are a couple of different ways that you can write this formula. In this case, p hat is the sample proportion, or p bar, and rho is the population proportion if you have it, but if you don't, just use the p bar. And then z is 1.96. Note that for a 90%, it's 1.645, and for a 99%, it's 2.58. So you might want to just sort of make a note of those numbers so you don't have to keep looking them up. The margin of error is this part. It's the part that comes after the plus minus. So it's z times the standard error. The standard error is this part, okay? So z times the standard error. And when we have like a poll that says X% plus or minus, Y% margin of error, then that margin of error is this whole thing, okay? So now you know what that means. So here's an example. In 2019, the proportion of uninsured people in the US was 8.5%. We're going to pretty much ignore that for now, but we'll come back to that later. Suppose researchers wanted to get a number for an update, and so they studied 10,000 individuals. So N is pretty big here. It's 10,000, and they found an uninsured rate of 7.7%. So P bar is 0.077, okay? And we want the 95% confidence interval, so Z is equal to plus and minus 1.96, all right? So our formula is P bar plus or minus Z, P bar, 1 minus P bar over N equals 0.077 plus or minus 1.96 times square root of 0.077 times 1 minus 0.077 over 10,000, which is equal to 0.077 plus or minus, turns out to be about 0.005, which on the low end gives us 0.072, and on the high end gives us 0.082. So we are 95% confident that the population proportion is between 7.2% and 8.2%. Do note briefly that 8.5% is not in that interval, okay? All right, so that one worked out. What about bootstrapping? So in your demo code for this chapter, you have code for doing the bootstrapping on this. What we're going to do is create bootstrap samples from the original data, and we're going to do it a lot of times, like another 10,000 times, to create many, many samples, and those will form a distribution. So like in StatKey, when we pull a sample and another sample and another sample, and then we can see how they're all distributed, this is the same idea, right? They're going to form a distribution. And then the confidence interval is from the 2.5 percentile to the 97.5 percentile, which puts 2.5% in each tail. So if you run through the R code, which you definitely should, you'll see that you get a bootstrap confidence interval of 0.061 to 0.094. That's actually wider, right? The low end is lower and the high end is higher. So that's a little wider than what we get from computing this. Here are another couple of examples. You ask 500 voters what they thought on question 2 for wastewater treatment facilities, and 274, or 54.8%, approved. What's the 95% confidence interval for this sample proportion? Do it, both ways. Do it with calculating and do it with bootstrap. And then another one, you have a friend that goes to school in Minnesota and they're interested in knowing what proportion of the students at their school are athletes. They ask 50 students and find out 22 of them are athletes. What is the 90% confidence interval? Okay, so your Z is going to change here. So stop the video and go work these out, then come back and continue on and see the answers. Okay, so the main election, doing it with the formula, the interval is 0.5043 to 0.5917. Doing it with bootstrapping, it's 0.504 to 0.590, so pretty close in that case. For the grad school in Minnesota, or your friend in school in Minnesota, um, with the student athletes, the 90% confidence interval doing it by hand is 0.3245 to 0.5555. And if you round that to 2 decimals, you pretty much get the same thing with bootstrapping. You get from 0.32 to 0.56. And there you go.